Hello, my name is Radosław Ziemann and I want to talk about linear time algorithm for geodetic problem in outerplanar graphs. Geodetic problem is one of the well-known NP-hard problems. It is related with finding the shortest paths, also known as geodesics, which play important role in many applications based on graph theory. First, let me introduce some basic definition. For some graph G, the distance d between two vertices u and v is the length of the shortest uv path. A geodesic G is any path of length d. Next, let S be a subset of vertices in G. Then I of S is the set of all geodesics between two vertices in S. Finally, a geodetic set of G is a set S such that I of S contains every vertex in G, and geodetic number G of G is the minimum cardinality of geodetic set of G. Here we can see an example of geodetic set for this graph G. It's easy to observe that every geodetic set contains leaves of graph. So in this case, we must add to the geodetic set S this leaf and this leaf, and we must also add this vertex to the set S. So finally, the geodetic number G is equal to 3. And we can observe that every vertex outside the set S lays on some geodesics between two vertices from the set S. On this slide, we have an example of outerplanar graph and maximal outerplanar graph. And a graph is outerplanar if it has a crossing-free embedding in the plane such that all vertices are on the boundary of its outer face. If addition of a single edge in G results in a graph that is not outerplanar, then G is called a maximal outerplanar graph. And here we can observe that if we added this edge between two vertices, this one and this one, this vertex wouldn't be on outer face of this graph. As I mentioned before, the problem is NP-hard in general graphs, but it's also NP-hard for ordered graphs or even for planar graphs. It cannot be also parameterized by the parameter tree width of G, but Mazzini in 2018 proposed a polynomial time algorithm for computing a minimum geodetic set in outerplanar graphs. Graphs with tree width equal to 2. Now I will show the main idea of the faster linear time algorithm for the problem in this class of graphs. First, given a graph G, we automatically have a maximal outerplanar graph H. In this case, the maximal outerplanar graph H is obtained by adding the dashed edges. Next, we must find so-called perfect elimination order, PO, which help us with traversing the whole graph step by step in linear time. Having this period, in this example from 3 to 9, we can construct a tree decomposition where each vertex corresponds to some triangle in graph H. So, for example, this vertex in tree T corresponds to this triangle with vertices 10, 8 and 9. So the idea is to traverse the tree T doing some proper calculation. After all the calculations for some vertex vi in the tree T, we have the partial solution for some subgraph of G. For example, after step 5 of the algorithm, we have the partial solutions for this subgraph. This slide shows us the main loop of the algorithm. For the graph G of order n, we have n minus 3 steps. And for each vertex vi in tree decomposition, we have 3 conditions. 1, 2, 3. If vertex vi is a leaf in tree T, then we must determine the partial geodetic set S of vi and the values C and D. These two values, C and D, are crucial for the algorithm, and I will talk about them on the next slides. If our vertex vi has only one child, then we update the partial geodetic set S of vi, values C and D, using the proper values for vi minus 1, so for this one child. Otherwise, we update the set S of vi, values CD, using the proper values for children of vi in tree decomposition T. Finally, after loop 4, we determine the set S, which is our final geodetic set, for the root VR of tree decomposition T, where R is equal to n minus 2. Mentioned before values C and D allow us to control some crucial cycles. It's easy to observe that if we have two vertices in geodetic set, for example A and B, and one path between these vertices is shorter than another, then we must add another vertex to the geodetic set, and this vertex must lay on this longer path. So C corresponds to the ordered list of vertices lying on some path and some cycle at the same time. On the other hand, the value D corresponds to the length of the geodesic between vertex on some cycle and some vertex in the geodetic set. So, for example, between this vertex and this vertex. On this slide, we can see the earlier example of graph G and some values of partial solution for V with index 9. H with index 9 is the list of vertices lying on the boundary face of subgraph G with index 9. So these all vertices from 11 to 9. L with index 9 is the list of vertices lying on path from left corner leaf to the vertex 11. And R is the list of rest of the vertices lying on this boundary. So it's the list from 4 to 9. Observe now that here we have some cycle without this edge. So we have the cycle 11, 2, 1, 7 and 9. So here is the edge between vertices from this list and this list. So the distance between vertex 11 and vertex from partial geodetic set is 2, and distance between vertex 9 and this vertex from the partial geodetic set is 4. Moreover, the size of the partial geodetic set is equal to 4. This vertex, this one, this and this belongs to the partial geodetic set, and we have two ordered lists, one for vertex 11 and the second for vertex 9. And this list corresponds to the earlier mentioned cycle 11, 2, 1, 7, 9. I omit the details how to join the partial solutions because it requires much time. In conclusion, the correctness of the algorithm directly follows from the induction on the tree T, and all the calculations can be done in linear time. Thank you for your attention.